Hello and welcome. Today, we're doing something a little different. We're taking a look at a railway map, something you've probably seen 1,000 times, and we're going to peel back the surface to reveal this hidden mathematical world underneath. We're using a really fascinating scientific paper as our guide to basically deconstruct the entire Indian railway network and figure out the secret rules that make it work so well.
So let's just kick things off with the exact same question the researchers asked. Imagine you've got a totally blank slate and you have to design a railway system from scratch. How would you connect thousands of towns and cities? I mean, it's a huge puzzle, right? You're constantly balancing speed against cost against convenience for the passengers. Let's look at two extreme ways you could do it, neither of which works at all.
Okay, so on one hand, you could have what they call the grand loop, just one single massive train route that hits every single station in the country. Sounds simple, maybe. No train changes needed. That's a plus. But the downside is insane. Your trip from Mumbai to Delhi might end up going through Kolkata first. Then, on the other end of the spectrum, you have the local link. Here, a train only runs between two neighboring stations. So to get across the country, you'd have to change trains at every single stop. Obviously, that's a nightmare. The real-world solution has to be something much, much smarter.
So here's our game plan for this explainer. First, we're going to completely rethink how we even look at a railway map. Then, we'll get the key vocabulary down so we can talk about networks like a pro. After that, we'll define what a small world actually is, and we'll look at the hard evidence for the Indian railways. We'll even uncover some other hidden rules of the network before we wrap it all up with a quick revision guide.
All right, first things first, we have to make a really big mental shift here. We're about to take that geographical map, and pretty much just throw it out the window. We're going to build a new abstract one based only on how things are connected.
And this is absolutely the most important idea to get your head around. We have to forget about physical distance. Kilometers, miles, they don't matter here. The researchers treated the railway as a pure network, where the only thing that matters is the journey itself. A connection isn't a piece of track. It's a route that a single train travels. This one idea is the foundation for everything else we're about to discuss. Okay, to make sense of this, you absolutely need to know these two terms. A node, that's the easy one. It's just a station. Simple. But a link, this is the really clever part. A link exists between two stations, say Station A and Station B, if there's at least one train in the whole country that stops at both of them. And notice, they don't have to be the very next stop for that train, just on the same route. These two things, nodes and links, are the Lego bricks we're using to build our new map. Okay, so we've got our nodes and our links. Now we need some tools to actually measure and describe the network they create. This is where we learn the basic language of network theory.
So our first key metric is the shortest path length, which you'll usually see written as the symbol L. In the abstract world of networks, it's just the minimum number of links you have to cross to get from one node to another. But what does that actually mean for you, the passenger, trying to get somewhere?
And here is the brilliant, simple analogy for it. The shortest path length is just the minimum number of trains you need to take to get to your destination. Think about it. If you can get there on a single train, the path length is 1. If you have to change just once, the path length is 2. If you change twice, it's 3, and so on. It's such an elegant way to measure how complex a journey is.
Now let's take that idea and scale it up. Imagine we calculate that shortest path length, the minimum number of train changes, between every single possible pair of stations in the entire country. And then you take all those numbers and find the average. What you get is the mean distance of the whole network. This one single number tells us, on average, how easy it is to get from anywhere to anywhere else.
And here it is, the first jaw-dropping result from the paper. The mean distance for the entire Indian railway network is just 2.16. Let that sink in. What it means is that to get from any random station to any other random station in the country, on average, you only need to change trains once. That is a sign of a remarkably efficient system.
All right, our next metric zooms in on the local structure. It's called the clustering coefficient. The best way to think about this is like a social network. If you are a station, this measures how many of the stations you're connected to are also connected to each other. It basically answers the question, do my friends know each other? Or, in this case, are the stations I can get to directly also directly connected to each other?
And the value for the Indian railway network is 0.69. Now that number might not mean much by itself, but trust me, in network science, that is incredibly high. It means the network is very, very tightly knit on a local level, with lots of little interconnected triangles of stations. If this were just a random network, that score would be way, way lower.
So, let's recap. We have a network with a very short average journey, about 2 trains, and very high local clustering. This strange combination of properties actually has a special name in network theory, and it's really the main discovery of this whole paper.
To get it, let's look at 2 basic types of networks. On one side, you have a regular network. Think of a perfect grid. It's got high clustering, right? Because your neighbors are also neighbors with each other. But it takes a ton of steps to get from one corner to the other. On the other side, you have a random network. Here, the clustering is super low, but because of a few random long-distance connections, you can cross the whole network really fast.
A small world network is the magical sweet spot right in the middle. It literally takes the best of both worlds. It has that high, local, grid-like clustering of a regular network, and it has the short average travel time of a random network. This structure is famous for being super efficient and also really robust. And we see it everywhere, from our own social circles to the wiring of the human brain.
Okay, so that's the theory. But where's the proof? Let's now look at the actual data from the paper that shows, pretty much without a doubt, that the Indian Railway network is a classic small world network.
So the first big piece of evidence confirms that short path length idea. The researchers found that, yeah, journeys are short on average, but also, and this is key, the average journey length doesn't just explode as you add more and more stations to the network. And this graph really tells the whole story. First, just look at that small inset graph. See that massive spike at L equals 2? That's telling you that the most common journey in the entire system requires just one train change. Now look at the main graph. It shows that as the number of stations, n, gets bigger, the mean distance grows logarithmically. That's that gentle curve. It's not a steep, straight line shooting upwards, which means the network scales beautifully. And the second piece of the puzzle confirms the high clustering part. Just like we suspected from that number we saw earlier, the local structure of the network is anything but random.
This graph shows that the clustering coefficient C of n hovering right around 0.69 for the full network. But here's the killer comparison. If you just took the same number of stations and the same number of links and connected them all up completely at random, you'd get a clustering coefficient of just 0.11. The real railway network is more than 6 times more clustered. That, right there, is the smoking gun for it being a small world network. Okay, so besides the whole small world thing, the researchers also dug into how connections are distributed. Are there just a few massive super hubs doing all the work, or is the traffic spread out more evenly?
So what this graph shows us is the distribution of connections across all the stations. And the key thing to notice here is the shape of the line. It's what's called an exponential decay. Now that tells us something really important. The Indian Railway network is not a scale-free network. You see, a network like the internet is scale-free. It has these massive hubs like Google that almost everything connects to. The railway system is different. It spreads the load more evenly, which probably makes the whole system much more resilient if a major station goes down.
All right, let's pull all of this together. Think of this as your final cheat sheet. Everything you need to remember from this deep dive. So here are the key numbers. The mean distance is 2.16, which means about 1 train change on average. The diameter, that's the absolute maximum number of changes you'd ever need, is only 5. The clustering, that really high 0.69. And that last value is pretty cool too. It tells us that big, busy hub stations tend to connect to smaller stations, not just to other big hubs. It's a design that really helps spread traffic across the whole network.
So this whole study basically gives us a powerful 4-step playbook for analyzing pretty much any network. Step 1, define your nodes in links. What are you actually measuring? Step 2, calculate the key metrics like the path length and the clustering. Step 3, use those numbers to classify what kind of network it is. And finally, step 4, and this is the most important part, interpret what that actually means for the real-world system you're looking at.
And we'll just end on this thought, which is kind of mind-blowing. Nobody sat down with a plan and said, let's design a small world network for India's railways. It just evolved into this incredibly efficient structure over decades of small, practical decisions. And that makes you wonder, right? What other complex systems in your own life, from your network of friends and colleagues to how information flows through your city, might have these exact same hidden mathematical rules running the show?